So welcome back guys. And before starting off this video, I just want to introduce again to our new OA series we just recently started. This is for people who are preparing for placements and internships, who are struggling to find good problems for the assessments. So this is a one go series. Watch this series entirely, and you will able to solve new questions which will come in interviews or online assessment. And these are all hard problems. You must try it. I'm definitely sure you will learn from each problem. Each problem will teach you a new concept, and it's a standard problem with a little bit twist. So do check it out. The link is in the description. So let's try to discuss today's lead code contest. Third problem, amazing problem, I would say. Another twist and turns as lead code does. The third problem, the dangerous. Two problem, too easy. This time they change the scenario a little bit. Now let's see, they make the third extremely difficult. That means it's very bad for the people who are average solving two questions. Them. So sorry for guys. But okay, let's try to read the problem. It says that subsequent sum after capping elements. Okay. You're given an integer array nums of size n and a positive integer k. An array capped by value x is obtained by replacing every element nums of I with minimum of nums of I comma x. What it's saying is, let's say you have 1, 2, 3, and let's say you are capping the by 2. This 3 will become eventually into 2. This will happen like this. And the further elements also, let's say, will be capped. They're trying to say that minimum of that. Fine. For each integer from 1 to n, determine whether it is possible to choose a subsequence from the array capped by x such that the sum of the chosen element is exactly. See, whenever you see subsequence, you should try to think whether here it is subsequent, really a subsequence that will come to it. But don't confuse with the term subsequence here actually. There's also a trick. They try to diffuse you some other thing, try to make the question hard, but it's not. We'll see the question is much simpler, but the constraints and the setting of the problem make it slightly difficult. And then the return zero base index array, which answer I depends that okay, if it is possible to make the certain sum I plus one sum or not. So basically we want to check that can we make it one, two, three till n sum or not. That the entire intuition of the problem. Just the slight twist that each time our array is actually changing, right? Because we are capping it from x, and x is the I, whatever I we are doing. Okay, so I plus one, basically one base indexing. So what this let's say this example. So for x is equals to 1, that means it will become 1, 1, 1, and 1. We want to make 5. Can we make 5? No. Hence it is a false. So let's see if it x equals to 2. So it would be 2, it would be 2, it would be 2, it would be 2. Can we make 5? No. Again it is false. Let's try to make it 3. So 4 will remain again 3 capped. It will be capped. 2 won't be capped. Why? Because it's already minimum, right? Minimum of 2 comma 3 is 2, and this is already capped. Now, can you make 5? Yes, you can. This one. Do you observe a interesting thing? Does this subsequent thing matter, or is it just subset? Actually, order does not matter. It's saying that order should matter, and it should subsequences that order matters. Actually, order does not matter. This thing should come to your mind first. Matter. Fine. Till here, all good. I think most of you must have think about that. Okay, order does not matter. That's fine. Move ahead quickly. We want to see the logic. Cool. Actual order does not matter. Fine. Then what does it tell you? We are here at k equals to 5, and then we are going to do that, and we're going a capping. Are you able to remind something, or you think something that similar problem you have solved? Similar problem. What you are essentially doing? You have a target. You have an some integer array. We want to check whether this target exists with some or no elements with this array element or not. It's nothing but subset sum problem, right? Standard subset sum problem. I hope you're recalling. It's not a subsequence, right? It's just a subset. Already told you when you remove the order from subsequence, it becomes a subset, right? So we defined that why it's not actually order does not matter, and then we made this problem and boils down into our subset sum problem. Now, can we solve this with the help of subset sum problem? Definitely yes. Why? You modify the array each time. according to the given constraint, like minimum of the thing, modify the array, apply subset sum, apply subset sum concept, boom, for each I, you will get the answer. What's the time complexity? What's the time complexity of this problem? Modifying the array, each time you have to modify the array, and we are going for each I, right? And then each, this is the ith loop, right? X loop, you can say. And then applying subset sum, target cross n, right? This is a time complexity required. In general, we require I cross target cross n, which is n cube. I hope you're getting it. N square is the time complexity of calculating a target sum. And for each I, you have to do that because you have to do this n times. Hence, the time complexity becomes n cube, which won't fit into this. Here, target is actually k. Okay. So, which won't fit into our solution. So, I think here till you should have think about that. At least you should think like this. Till n cube solution, you must have thought about it. If you have solved good question, no worries. If you haven't solved it, subset some problem. Do check it out, the subset some problem. I will also put the link in the description. Do solve that question first, then come to this problem. Okay. I assuming that you have solved the subset sum problem. Let's try to deep dive into it, what it actually does, and how can we solve it. See, here the problem is the array is changing. Array is changing. That's the only problem, I guess. If array was not changing, then no problem. Directly you can return using the subset sum. Also, can you tell me what is the DP state define the subset sum? This is the beautiful problem. Why you should know the the DP state. This DP state defines that till ith index, till ith index, can you make j some j, sum equals to j. This is this defining. You can define it's a boolean array or an integer array. Does not matter. 0, 1 array or boolean array you can define. And we just need to check whether can you make till the sum j using the first I elements. Right? Okay. That makes sense. Cool. So see, do you see a property by the way that the given elements we are given, let's say given with 1, 5, 3, 2, 4, and what we are essentially doing, we are capping it, right? Firstly we can making it 1, 1, 1, 1, 1, then it would be like 1, 1, 2, 2, 2, 2, and then it would be like 1, 5, 3, not 5, sorry, 3, 2, and 3, sort of. And I already told you order does not matter. So is it better, somewhat better to sort it? Why? You should think at every step why each step is important, because then only you'll be able to solve the problem. Okay, why I've sorted it, I already explained why. Because the order does not matter here. So it's good to have a knowledge that okay, the next element is sorted. And how does it help? Let me just explain you. Let's suppose somehow you find out the first index, which is 2. Somehow you determine that okay, which index is 2. And then, can you tell about the further indexes? Can you determine? Yes, you can. Why? All elements after the first two, after the first two, will be 2. Why? Capping is happening, right? And how would you find first two? Very simple. Lower bound, binary search, right? We'll find the first two using binary search. It's a good problem. It's involved DP. It involves binary search. It's a good problem. It involves basic concepts, but combinedly it makes a good problem. It's like J advanced, right? So yeah, it doesn't matter. But okay, cool. Till here we are all good, right? We have saw the pattern. We can determine an array after a particular time. We sorted the array. We know some variation of subset sum is required here. The problem in the subset sum is I know till n square. I can calculate the n square dp. That till ith index I want to make some k. That's fine. That's fine. But now let's try to think about like this. Okay, can we reduce that array copying part, that we are maintaining another array again and again, right? Instead of that, can we do some better? That let's try to see. let's say you calculated that index where it is changing, right? To here it is changing. Okay. What we will do till index minus 1, till index minus 1, we gonna create some sum. Okay. Here there is some k minus sum. Okay. There is some sum and there is some k minus sum. Do we know some something about this sum? The right side part, like what, how it is maintaining? Yeah, we know that it's a multiple of our capped value. It could be either x, there could be 2x, could be 3x, till some multiple of, let's say, px. Agreed? Why? Because it could be two, you can take two elements, you can pick three elements, you can pick four elements, and there obviously there is a range. Here basically here is a range, right? Four elements is a range. 2, 4, 6, 8. This is the variation. Okay. Corresponding to this thing, can we the create a leftover sum before index minus 1? What I'm trying to say is eventually we have to make k sum. Okay. We are dividing into the parts. Let's say what we did, we divide firstly x, and the remaining sum here which should be k minus x. Or it could be initially with k also, it should be 0, it would be k. Or either it would be 2x, here it would be remaining is k minus 2x. See, this step I will tell you how to do it. Do you understand this step? That we are defining the sums like that. And if you get the hint till here, can you understand? Can we calculate this with our DP table? To calculate this sum, particular sum, DP of the index minus 1, what we have got it, and the sum k minus, let's say, some pi, not p, but let's say some q. Q varies from 0 to p. Did you get that? What I did, I created some from the right hand side. It could be 0, it could be x, it could be 2x, it could be till px. And I want to create the leftover sum using this index minus 1, the left part, index minus 1, and the sum remaining, which is k minus qx. Qx can vary. We'll run a loop from 0 to p. And then if you saw that we reduce our complexity, we'll run a loop for each index from 0 to n minus 1, and we'll again run a loop for an index from 0 to 2p, and this will vary for each index. This p varies for each index. Did you get it? That what we are essentially doing? Do let me know in the comments. If you have any doubt, do let me know. Okay. What I essentially did, what was our initial thought process? We can calculate our DP using the same DP table, DP of ij till, you know that, right? Subset sum equals to k. Solve for that. What you will get for the entire array, that for what particular index, what sum you can create. You can create a boolean or whatever. Now you will leverage this DP here by running inside this loop. We'll check it. Okay, whether I can create this k minus qx sum or not till index minus 1. We'll find that index using the binary search. We'll find this sum. We'll use the DP which we previously computed, and we'll check if it is possible for any range. It is possible, any value possible. So what we'll do, it's very simple, right? Answer of I, we'll mark it equals to 1, and then we'll break it. Why to go for more loops? Yeah, we found it for particular I. Or if it's not possible for all the particular ranges, then we cannot do anything. Let me just also show you with the help of example what I'm trying to say. With this same example only, 4, 3, 2, 4, 5. Okay, we'll see. 4, 3, 2, 4, 5, right? 4, 3, 2, 4, and let's say k equals to 5. So what we gonna do? Firstly, let's try to create a DP table. Okay. So how a DP table look like? I know you know that. I'm creating a DP table of zero base indexing, not one base indexing, sorry. So here it's like DP of ij, and the column represents the sum, the ia row represent the this indexes. Okay. So 0, 1, 2, 3, 4. I'm creating one base indexing. Okay. And this is like 0, 1, 2, 3, 4, and 5. Quickly, let me just write the DP thing. So 0 sum till zero index, what will be the answer that you want to create? You don't take any element, right? It would be always true. Take all the elements till zero sum, and till zero index, you don't take any elements. It will be always one, right? Zero sum. Zero sum is always present. Don't no take any elements. Now one, is it possible? No, it is not possible. Initially, all things are defined by zero, and then we'll check it. So is also will sort it. Very important. So I already explained you, right, why we sorted it. We'll create this DP table on the sorted array itself. Then it elsewise it will create the problem. Okay, we cannot make it. Can till zeroth index can we make two? Yes, we can make two. Can we make three? No. Can we make four? No. Can we make five? Fine. Let's try to make till one index. Can we make one? No, I cannot make one. Can we make two? Yes. Till this index, can we make two? Yes. You can pick two. Can we make three? Yes, you can make three. Can you make four? No. Can you make five? Yes, pick two, three, both. Right. So what we are essentially our DP states looks like. Either you pick, either you don't pick. DP of ij is equals to DP of I, whatever I minus one j, or dp of I comma j minus nums of. Obviously this should be greater than 0. This is our DP state, right? I hope you remember from the DP lectures that you take either pick this or don't pick this. Pick this current element or don't pick this current element. If it is not greater, then obviously only depends on the I minus jth part. So here, how it we pick this? See, here it is 3, right? So we picked dp of ij. We want to compute this. We will calculate 3 minus 3, 0. So this is already we have this. That's why it come 1 from here. Okay. So try to make it dp on yourself. This will be 0, 0, 0, and I will quickly fill up the dp table. This will be 1. And yes, you can make as always above. Can you make it 4? Yes, you can make it 4. Can you make it 5? Yes, you make it 5. Can you make it 1? Now all things will be 1 itself, because above things are 1 itself. So 1, 1, 1. So I hope this DP table we made it. And now what we are essentially doing is we are capping it. Now we are capping it. We have this DP table. Now what we're doing is we'll calculate. See, now we have what? 2, 3, 4, 4. This 2, 3, 4, 4. Now we'll go with 1, the sum as 1. So what is the index which is higher than that, which is 2, right? So that means all will become 1 in this case. So our index which we are finding is 0. Okay, this index will be 0. And then total number of whatever the p I told, which will be n minus index, which is equals to 4 here, right? We can go up to 4. So what we can do, we can try out all the sums, right? We can try out that you can pick either nothing from here. You pick 0 into 1 and remaining k, and you can pick dp of 0 index, 0 minus 0 minus 1, index minus 1, right? So since we are doing here at one base indexing, I hope you're getting it. We are doing it here at one base indexing. So dp of 0, and then we will check with firstly what? 0. We'll check k. Can we make k with 0? I don't think so. We can make 5 with 0. So yeah, we cannot make it, right? So we cannot make it. So it is not possible. Then we try what? Then we try 1. Let's define k minus 1. Can we make 4 and take 1 from here? What we are doing? Can we make 4 and can we took 1 from here? Then I will take 3 and take 2 from here. And then till I make how many I can make? I can make till 0. And here we can take 4. 1 into 1, 2 into 1, 3 into 1, 4 into 1, right? But all will be 0, right? But this we can make at max 2 we can make. But can we make 1? We cannot, right? We cannot make 1. So that's the entire intuition, that we cannot make 1. Fine. Then what we do? We'll start with 2. Can we make 2? That's our thought process, right? Using 2, can we make 2 at least? So let's try to make 2, 3, 4, 4. And then what we want to make, using the same things. What we initially have, Now we will cap it. We'll cap it with 2, 2, 2, and 2. Okay. We'll cap it 2, 2, 2, 2. And can what is the target sum we want to achieve? We want to achieve 5. Can we make 5 from this case? I think you can directly say no, right? We cannot make it because 5 odd is there, right? We cannot make it. And then the next thing is 2, 3, 3, 3 for 3. Now it's very interesting. Now it's very interesting. You found out this particular index as the first index that is gonna changing, right? So you gonna go till this index, you can go up till this index and you can try out. So let's say you take nothing from here, you take 0 from here, all 5 from here. Is it possible? No, it's not possible. You take 3 from here. Can you make 2 from here? Yeah, it's definitely possible. So you pick this and you finally return 1 for it. That's how you're gonna do it. I hope you get the entire intuition. I also dry run the whole example for you. I made the DP table for you. Let me just go you through the quickly through the code part as well. It's quite simple. It's not difficult. It's just the entire intuition. We just sorted the array first, right? Then we created this perfectly DP table. I hope you know that how to create a DP table of subset sum equals to k. Do check it out the problem if you don't know it. It's no problem. Then come to this video. We created this DP table, right? I just explained you the two states is possible. Either you pick it or either you not pick it. You can, if the sum is greater than this, you can pick it. This is no pick state, right? If it greater than the 0, you can pick it also. So this is the, and why we are doing I minus 1? Because this is one base indexing. That's why we are doing that. Then we calculate the index, first index. How we calculating the index? This is the cap. What is the cap? Cap start from 1 till n. So we'll start finding the index. Now it's very, very important what I did here. I calculate the max use. What is the max use? This is the P here. How many elements we can go through? We can start count from 0 till the max use we can go, and we can go till count plus plus. See, and now I already told you the right side sum we are calculating from count into cap. This is the right side sum. The left side sum remaining is k minus this. Can we make? Obviously, remain should be positive. The sum should be positive, and this is also should be there. This is C, very, very important. We already, this index minus one, we already did. Why? Because this index is zero base index. So I hope you get it. We already did a minus one here. So we don't need to explicitly write minus one. That's important thing. And the remaining thing, if we can make it, then we can finally write answer of cap minus one equals to 2. We'll just break it out because we don't need to go further. So it's a very beautiful problem, a good variation of a subset sum problem. If you have solved that problem, you must have liked that problem and this solution as well. So do let me know if you understood everything. If you don't, do let me know in the comments. I will tell you, and do check it out the way series as well. Stay tuned for the further updates. Bye bye.